Okay, so we're getting into the next chapter. This is chapter 17. And we're going to still be dealing a lot with rotation of objects. Um, but we're going to sort of start to get into some things about acceleration and Newton's law when we deal with rotation of objects. Now, when we talked about energy or force and involving an object with linear motion, we always talked about mass, okay? And the mass was really important. What happened there? So if we want to talk about the acceleration of an object, we had Newton's law, so F is ma. And we know that the more mass you have, the more force you're going to have in order to get the same acceleration. We talked about energy. So kinetic energy, for example, okay, with 1/2 mv squared. All right, and internet's just a little bit glitchy here, so hopefully it's not going to be too clunky. Again, so the mass is an important term in there. Now, when it comes to things rotating, we have similar equations and exactly the same ideas. So if I'm going to talk about an object accelerating, I can have Newton's law, which is mass times something times alpha. All right. Or if I want to talk about the kinetic energy of an object, I could have 1/2 times something times omega squared. All right. Now, what's the thing that goes in there? Well, look here. I've got a mass and a mass. So instead of thinking that as a mass, think of it as an inertial term. It has to do with what it takes to change the state of motion for the object. Rotationally speaking, that is what we call the moment of inertia. So Newton's second law with the moment of inertia is m equals I alpha. And kinetic energy would also be 1/2 I omega squared. Okay. Now, the moment of inertia, it has the same function as mass, but it depends on two things. It depends on the actual mass of the object, but it also depends on the shape of the object. Okay, now we haven't seen that before, but now it's important. We've never really dealt with the shape of our objects, but now we will. Okay, and so let's take a look here at some different geometries. Okay, so this guy right here, let's take a look at it. All right, I don't know if I can. All right. So I equals mr squared there. And so m represents the mass of the cylinder and r represents its radius. Okay. And you can see of the two terms, r is squared. Okay. So distance from an axis of rotation is going to be very important. Okay. Now, what I have for you here on this sheet is just some examples of geometries. There's lots of different tables of moments of inertia like this that you can find. This is just one. I've left some links for you inside of eLearn to take a look at to get a little more information about some of this stuff. In calculus class, or maybe we did some of this even in statics, I don't remember. You might go through and say, derive. How do we know that the moment of inertia of a sphere is 2/5 mr squared? Where does that come from? And if it's a hollow sphere, if it's just a shell, it's very different. It's 2/3 mr squared. It's higher. if all that mass is concentrated further out from our object, okay? So a couple other things, the little boxes on the top. Let's start up in the right-hand box up here, this guy, okay? This is called the parallel axis theorem, and I'm going to show you how that works in our very next example. Okay, so just sort of put a pin in that for right now. This guy right here has to do with what we call the radius of gyration for an object, okay? Now, the radius of gyration is similar to center of mass. Center of mass we need for translational stuff, okay? It's moving from here to here. The center of mass has gone from here to here. That means that I could treat it as if all the mass were concentrated in that one spot and that one spot relocated. Now, in a rotational sense, we have the same thing, except it's not the center of mass that matters. What matters is the radius of gyration. So the radius of gyration is as if all the mass were concentrated into a single point, and that point is rotating, and we're interested in the rotational behavior of the object, okay? And we use the letter K, or at least just your book uses the letter K for it. And K depends on the moment of inertia, as you can see there. Okay. So let's take a look at an example. Okay. And this is the kind of thing we're going to be doing. We are not at this point interested in you proving your calculus prowess by doing complicated three-dimensional integrals to find the volumes or moments of inertia. You can actually only do that for a certain number of nice geometries. Then you run into some problems, okay? So what we're going to do is we're going to be treating these different objects as pieces, and we'll put the moments of inertia together just like we would mass, okay? So if I've got a 2 kilogram block and a 5 kilogram block, I can consider those to be one 7 kilogram block. We can do the same thing with moments of inertia. They're going to add up for us. Okay, so we've got our situation here. I want to put some numbers on here for us just so we can have a little more to work with and actually get some numbers. And so let's suppose, that the mass of the rod is actually 2 kilograms. And let's assume that its length is 1.5 meters. And then for the sphere, we're going to say the mass of the sphere is just 1 kilogram. And its radius is just 0.15 meters. All right. So to get the total moment of inertia, what we have to do is we got to take this like one piece at a time. So we'll do the rod first. Do the rod first. So all we have to do is just plug it in. So it's 1/3 m for the rod, the length of the rod squared. And when we put our numbers in there, we got 1/3 times 2 times 1.5 squared. Now I did this on my calculator earlier, and I got 0.375. Okay, now let's talk about units real quick, because the units for moment of inertia are nothing fancy. It's just straightforward yuck. Well, it's not too yucky. But we've got kilograms and meters squared. All right, and you can see that that's just exactly what we have in our equation, right? Kilograms meters squared, right? There's no shortcut thing for it, so we just got to say kilogram meters squared. If we were at SI units, we might have slug feet squared, something like that. So that one would be a little rough. Okay. All right. So then what we're going to do is we're going to come back here and we're going to get now, we're going to do I for the sphere. Okay. Now the sphere we're actually going to do in two parts. I'll explain why in just a second. No, I'll do it now. Okay, we have to do the sphere in two parts because the sphere is not just rotating, okay, as the thing goes around. All right, well, I don't know which way to do it here. As that thing goes around, the sphere is going to rotate. So if the whole thing spins and makes one rotation, the sphere itself has made one rotation. Okay, so it's rotating about its own center of mass as it goes around, plus it's rotating about the axis of rotation. So with the sphere, we need to realize it's like we've got two rotations going on. So let's get the rotation about the center of the mass first. Oops. Okay, this was for the rod, by the way, for the rod. So now we're going to do I for the sphere, and I'm going to call it C, as in its own center of mass. And that's just 2/5 mass of the sphere, radius of the sphere, squared. Okay? So we plug in our numbers. We get 1.15 is our radius. And I calculated this earlier, and it's pretty small. 0.009. Like that. Okay, but like I promised, we've got to come back and do the movement of the sphere in a circle. So it's spinning and it's moving in a circle. So the way we treat that, I'm going to call that I sphere parallel. Okay, we treat it like a point mass moving in a circle. And the moment of inertia for a point mass is just mr squared. So in our case, we've got m for the sphere. And let me not call that big R, let me call that little r squared. Okay, now we have to go from the point of rotation out to the center of mass. So there's R right there. Okay, so if we plug that stuff, work all that out, we get mass of the sphere, and then we're going to have L plus R quantity squared. So mass of the sphere, oops, I wanted to put a number on that, is just 1. And then L was 1.5. R was 0.15 squared. Okay, and I calculated that earlier, and I got 2.732. Okay, so that's odd. Well, maybe it seems odd. I mean, look at the moment of inertia of the sphere. The rod. The moment of inertia for the rod was 0.375. And the moment of inertia due to the sphere moving in a circle is much bigger. Much, much bigger. Okay. Now, compared to the moment of inertia for the sphere rotating itself, 0.009, that's super tiny. Okay. So in our composite object here, composite means it's made of different things, of course. In our composite object, the most important part, mass inertia-wise, is the sphere going in a circle all the way around. Okay. That's the thing about moment of inertia. The mass that's furthest away from the axis of rotation is the most important of those things. Okay, well, let's put it all together. So my total moment of inertia is going to be I for the rod plus I for the sphere around its center plus I for the sphere traveling as a point mass in a circle. And we just add all those things up. So I've got 0.375 plus 0.009 plus 2.732. And I'm going to put those things together to get my total. And what I got was 3.107, and that's kilograms meters squared. Right. Now, when I get ready to, if I was going to put this into mastering or something like that, I would, of course, need to truncate it to 3 sig figs. And so then I'd have something like 3.11. Okay. I think it's a pretty good habit to keep track of 1 extra sig fig as you go. If you're going to be writing them down, I mean, if you could keep all the digits in your calculator, that's probably best. But probably what is sufficient is just to keep track of when in other words, when you write it down on your paper, do 1 extra digit. That'll be fine. That'll be fine for you. Okay. So we get 3.11. And the biggest contributor of that is the sphere moving as a point mass in a circle. Okay. So let me back up real quick. We're almost done with this one. I want to go back to the parallel axis theorem, okay? Because we just used it on our sphere. What the parallel axis theorem tells us is if we've got an object that's not just spinning, but it's sort of orbiting, so to speak, then we need to calculate that as the spinning part plus the orbiting part. Okay, the spinning part plus the orbiting part. And we're going to see a lot more examples of that as we go along.